recording is started.
Yes.
So I think what I would recommend is that we stop looking at simulink and use the last few minutes of our time together to see the remaining material that I have very high level. I want to show you just a couple of different things. You know, I think you should continue debugging. Maybe unless I can add the ordered angle conversion and see if she gets a different result.
Yes, not the ordered angle.
You did?
Yes. Of the body body with respect to the LVMH, and theta oscillates around 15 degrees.
Ah, can you show who you are? So it's not going crazy at 90 degrees?
No.
Okay, that's pretty good. That makes sense. It's one orbit?
No, these are 3 orbits.
3 orbits.
And of course, these are degree and not radians.
I hope so. Okay. So maybe you guys can compare codes and see where the mismatch is. I'm sure it's something minimal, even though Darius' quaternion error, it doesn't look something that should be unstable. It's a constant quaternion, it's constant one almost, and then the other, there's one component that oscillates, but I don't know why it's coming out that way. But yeah, you're getting there. So it's definitely a matter of initial conditions. You don't want to be too much far away from. The one thing that you can play with, for example, now that you have it working, is keep reducing that 0.9 coefficient on the initial motion until it breaks. It's basically seeing when things are not linearizable anymore. And mostly what's happening is that the LVLH, I guess, is fast enough for your angles to grow outside of a linearization interval, and so the analysis doesn't apply anymore. Make sense?
Yes.
Okay. So
sorry, Professor. So
yeah,
the initial condition should be not perfectly. I mean, the angular velocity should be not perfectly the one of the LVLH.
So I think what she has is the 0.9. It's 90% the one of LVLH, but that 0.9 was applied, as you may recall, was applied before you converted into inertial.
Yeah. Indeed, I did the same. But the point was that if I put exactly one, at least me, I have a stable behavior. I don't know if let's try it, but that's.
So if you put one, it's stable.
For me, it's not stable. It was not stable.
Oh, but that's not.
Yeah,
I thought we had run that case. It's the case when it was perfectly aligned, actually.
No, so yes, sorry, I made a mistake. If it is 0, I mean, it was not stable because we now agree that the initial condition should be the one aligned with the.
Yeah, that's what we're doing right now. It's you start aligned, but you're a little bit slower than LVLH, and that's one way. You can also start with the same angular velocity of LVLH and a little misaligned. Maybe you can play with different initial conditions. The goal is seeing the oscillation, and in order for you to see the oscillation, you need to be, you need to have a non-zero relative motion with respect to LVLH. So you cannot be perfectly aligned and also moving the same exact way, because then there is no. You're not exciting the pendulum behavior, in other words. But if you excite the pendulum behavior, you need to do it carefully so that it remains small enough that you don't go outside of the region of being able to say that it's stable, right?
Perfect. Okay.
Yeah.
Nice.
And I cannot quantify that. I honestly do not have. I think it depends on the on many different things, but I would say a few degrees, no more. and probably if you put 0, 0, 0 for your initial angular velocity, the LVLH angular velocity, even though small, after a few minutes, has moved your your relative Euler angles to an interval which is big enough to throw away all the linear analysis. Yeah. Okay. So I think you're doing just fine. It's just tweaking things here and there. I want to just very quickly go over this last material that I put for today without really digging into the details, okay? But I have, let's see, I also want to upload some code now that I'm thinking about it in there. Well, first of all, let me share my screen. So, okay, that, not this one. Just 1 second. So the slides that Camilo presented are on the same folder. And this is the material that I had for today. And as I said, I will just go quickly. But basically, the idea is, okay, let's simplify things, because in general, you will have to do an astral model of your spacecraft to compute the modes and the frequencies. You really don't want to do it by hands, except for very special and simplified cases. And so this represents pretty much what I showed you in the video: a motorized hub, basically a spacecraft, if you like, which is the green one, that can only rotate about its symmetry symmetry of the axis of the cylinder, and the torque is U, its radius is R, JH is its moment of inertia about that axis, and then you have a flexible arm that has a mass T with moment of inertia JT, standing for tip. You can write the kinetic energy of the entire system, rotational plus translational plus the one that has to do with the continuum, which is the integral that you see from 0 to L for the linear velocity. Rho is the density of the beam, and then this is the term that has to do with rotation, which changes according to where you are along the beam. And then this is the potential energy that only has to do with, of course, the flexible part, which is the beam itself. And so if you basically follow what we saw yesterday, using the finite element approach to the Euler-Bernoulli beam, you have your shape functions L1 through 4, and you can eventually write your discretized model for the system, where the mass matrix has components of diagonal that represent the rigid elastic coupling terms. Basically, the torque acts on the beam due to the rotating hub and vice versa. The beam itself flexing will act with the torque on the hub because it's flexible, and so these are the expressions that you get. In particular, the matrices are given as these in these forms, and you can going manually through the same processes that we seen yesterday. You can show that these are the individual elements that go into those matrices. It's not a crazy exercises, but it's definitely tedious. And in general, as I said, it will be done for you by some software. So again, these are the equations of motion. You decouple the modal analysis that we have seen to diagonalize the matrices, basically. And so in the new state, you can find a matrix that has on the diagonal the frequencies, the natural frequencies of the system. And also, if you want to add some damping, well, you're more than welcome to do that, but that's something that we have to make up or measure through experiments. This type of representation can be put in the linear state space form, like a linear time invariant system, And so, bottom line is that if we consider one motor, one link, the goal would be to control now the orientation of the hub, but at the same time, what the tip mass is doing. If I go back to the example itself, you can interpret this as a spacecraft that is trying to reorient an end effector. Maybe there is something here that needs to grab another spacecraft. And so your goal is reorienting yourself, but also, since you only can act on the hub, what do I do to manipulate the position of the tip mass in an intelligent way? And maybe the intelligent way is just that you want to reduce any residual vibration after the reorientation, as we've seen in the videos, and that's a good enough goal. But you have to do it with just one control variable, which is the torque on your hub. And so for feed forward, really we're not doing any feedback control, but basically what you're going to do is this. You have a reference motion for the hub. So you want that to be reoriented, I don't know, 45 degrees, and you would like to do it maybe time optimally. So if everything was rigid, you would do it in a bang bang, but you can't. And so you filter that through some feed forward controller, something that, in fact, we're calling them filters, something that modifies the reference, the desired ideal rigid signal to make it aware of the fact that things are actually not rigid, and I have a model to represent the flexibility. And then if you want, you could have a feedback controller that would make things a little more elaborate, but we're only going to see feed forward, so this would not be there, not even the feedback here. So no details about this, but two different types of approaches. One is smoothing the signal. So in other words, say that my reference is a bang bang, as I just said. I want to reorient my hub, and I want to do it as fast as possible, so I do maximum torque in one direction and then maximum torque the other direction to slow down and stop. You can smooth that bang bang and make it look like you see in this graph by adding some rise time at where you will actually see the step functions, okay? And so this is a mathematical form to do that, where you decide, okay, I want to reach, say, from 0 to the maximum torque. I want to reach it in a certain interval of time, delta t, and then go down in 2 delta t to the minimum torque, and then go up to 0 again in the same amount of time. And so these are the equations that give you how you would reshape the bang bang and the new calculation of the final time, which is, of course, longer. If you were doing a maneuver that is exactly bang bang, it would take less to reorient everything, but in this case, you cannot. And this is actually in a thesis from my former advisor, postdoc advisor, Professor Romano, who's at the Naval Postgraduate School. He used this technique for some experiments. The other one that I showed you actually in the videos, and I have a simulink file that runs this, is input shaping. Instead of taking the bang bang and smoothing it like you've seen before, you perform a convolution of the original signal, the bang bang, so basically a maximum torque, then minimum torque, nothing in between. Instead, you do a convolution with two or more impulses. You can have more than one. The original one, again, no demonstration here, that you see in literature is with 2. Then there is a more robust version that has been proposed that has 3 impulses. And these are the k that you see in the amplitude of these impulses are given by the exponential of minus zeta pi over 1, a square root of 1 minus zeta squared. That's the damping of your system, and then where they are in space is basically given by this other quantity, which is delta t, and the omega 0 is the frequency that you were saying we want to kill, that you want to eliminate. And so if I am focusing on the first mode of vibration of the flexible link, the first omega, which is usually the one that is the most important because it corresponds to the highest deformation, then I design the input shaper to do this. And we'll see in terms of the signal what it actually means. It means this. You have a reference acceleration. Again, this would be your bang signal, for example, and you convolute it with the input shaper. So you're basically going to change the amplitude and the timing of these new constant signals, because f is the reference initial signal, okay? And so you're going to modify the amplitude of that, and you're also shifting in time when f is executed, basically. And these are the modified amplitudes that you get. So basically, the convolution results in a three time-shifted copies of the input. The impulses are never sent to the plant. This is basically a filter. This is taking the reference bang and it's spitting out something different. So since I said I would go high level, I'm just going to show you a model that does exactly that. And I'm going to upload all this into the same folder, if I ever get to move this to the right window. Okay. So this is a very simple model that simulates here the hub plus the flexible appendage and final tip with two final elements. So it's very simple inside. It's a matrix multiply and a K matrix that comes from an initialized file that I have to run, and a mass matrix that has to be initialized. I don't know what this is. This is just a vector of 5 components. Anyways, we don't really care. You can more than spend time on looking at the details. But basically, I have an initialized file that, or main file that you have to run first. Okay? It's a pretty long one. You have the mass of the tip, J of the tip, etc., all the variables, the maximum torque. And then you start putting together the components of the mass and stiffness matrices. You find the frequencies. And let's see, what do we have here? Okay, so now we start shaping the signal. So you see, this is actually the bang, and we plot it, and then we start playing with the different input shapers. This is the first version, and I believe I have a second version with an error. 5% error in the omega, and let's see, and a 5% error in the other direction for the omega. So if I run this, it's going to show you, okay, the different acceleration profiles, or torque, rather, if you like, torque profiles that I'm going to give. Well, it's actually in terms of acceleration, so angular accelerations. So you start from this. This was my initial signal. This is what I wanted. I wanted in about 2 seconds to reorient my hub, ignoring the fact that there is something flexible attached to it. And then you realize, well, I can't do that because it's going to result in one of those videos that we seen yesterday where things are going crazy and oscillating. And so, okay, this is the input shaped bang when you use just one frequency. The first frequency, the first mode. So this is really what the impulses are going to do. They're gonna, as you can see, rescale the bang values. In fact, you get to that almost 0.8 only for a short amount of time, and same down here, and they're shifted in time. And this would be an input shaper when you assume that you have knowledge of a frequency which is a little bit inaccurate, 5% less, and this is 5% more. And so I want to see the effect of these different shapers. So I take this model and I run it. So this is the reference signal. So this is what I get when I have bang for that type of flexible system. I run it and I look at the theta, and the theta is going crazy. As you can see, it's not really looking like it's been reoriented to any value, it just keeps going. And that's because there is a residual vibration that I haven't even considered. And as I said, in the equations of motion, you have those terms m in the mass matrix, m theta q or mq theta, that are basically telling you, okay, I apply a torque to the hub that is going to excite my flexible link and apply a torque to it, but vice versa, the flexible link is moving back and forth, that is going to apply a torque on the hub, and that's why things are not going anywhere. So this is the bang. Then for the first input shaper, where I have perfect knowledge of the frequency, I have to change this and call it export S1. That's the vector that comes in. And I also have to, these are the instructions, TFS1. It's a little bit longer, right? It's a longer maneuver. I'm running it for 100 times that, because this is very short maneuvers and I want to see the long-term effect, of course. But just
sorry, Professor,
yeah.
Before running, I think I cannot see the scopes. The one that you have, yes, this one.
Oh my goodness! I'm sorry.
Okay, now yes.
Yeah. So this again.
Thank you.
Good thing that, yeah, thank you. Good thing I didn't run it. So of course, this is a terrible way to show plots. I hate scopes because they come with no units and no names on the axis. But anyways, this is a residual vibration with bang. It's just there and it's pretty important. And this is the theta behavior, the angle of the hub that I wanted to reorient, and of course it's not really stopping. It's not, starting from 0 and going to 45 degrees. It just keeps going because I ignored the frequency, the first frequency. Now instead I have a bang, an input shaped signal. I'm running it for 100 times the actual end of the maneuver just to see how things look like, and it's done. And my angle, well, still growing, but it's getting there. It's definitely less oscillations, but there is a residual drift, unfortunately. And then the residual vibration is definitely less. And again, this is feed forward. So and I'm using the first frequency only. So I'm targeting that one. But definitely there is less residual vibration. Then let's see. The second one is with the lower error for frequency, S2, and I have to change the time to be S2. And I run it. And let's see what this looks like. Yeah, expect it to be worse because now I'm still trying to take into account the frequency, but I know it with less accuracy, and it's getting a little uglier again, but better than just the blind bang. And lastly is the one that has an estimate that is a little too high for the frequency. And it goes back to killing the frequency. I mean, you're being conservative. You think that there is more flexibility, and so you're definitely doing a better job on the oscillation, but you're only focusing on the first one. So you could shape your bang taking into account more frequencies and basically try to avoid this initial behavior, because this is really what's causing your misalignment and drift at the end. So, but this is in a very short amount of time and in a very simplified model, the effect of flexibility on a system that has to change attitude, that has to change orientation. And this is one potential way to attack it, is being aware of the modes of vibration and try to reduce the excitation of them in the design of reference signals. And this is open loop, wasn't even feedback. And I think, I've given you enough for a much longer class. Do you have any questions on these? I'm gonna share this software in the same folder in case you're interested. No questions? Okay. Where is Teams? I can find Teams. Okay. It looks like we're almost done. I'm going to stop here. Again, a refresher that by Friday of next week, I would like to have your assignments delivered. In terms of getting stuck with those, I suggest that we either, why don't you put an announcement, send me an email and also put an announcement in Teams, so that if I agree to meet with a student, the rest of the class maybe knows as well, because it could be useful for more than just one person. Does it sound like a plan?
Yes.
Yes, okay.
Okay.
Thank you.
Okay. Well, I hope this was informative. Maybe not useful for your research. I don't know. I hope there were some things that were new, and I want to thank you for giving me the chance to teach this class. I was really hoping to be there, but maybe for future classes and for other opportunities. But thank you so much. Any last minute comments, thoughts before I let you go? Thank you. I would invite you.
Just thank you.
I would invite you for a cup of coffee, but we need to take a rain check, as they say here. Postponed. My plan is actually to still come if things calm down, and I was really thinking the first 2 weeks of May at this point. I mean, things should be reopened by then, right? Maybe. Okay. Stop recording.